Chapter 5, Lesson 3, Part 2 is more on solving trig equations. Before I get into some additional trig equations to solve, I just want to take a moment to talk about angles. So you guys know that an obtuse angle looks like this. And my question for you is, why are obtuse angles always so unhappy? And the question is because they're never right. Right angles look like that. Good stuff, huh? All right, a little Algebra 2 review. If you go back to Algebra 2, you solved problems like this. And the one on the left is a fourth degree polynomial that can be solved like a quadratic equation. You would have to put an x squared at the beginning of both factors. And then you'd ask yourself what two numbers multiply to give you the constant -3, add up to give you the coefficient of +2 in front of the x squared. And that would be a +3 and a -1. Once you get it factored, you could set each factor equal to 0 and get your solutions, which would give you two real solutions, plus or minus 1. And when you set the other factor equal to 0, you'd get two imaginary solutions, plus or minus the square root of 3i. So that's a little review on Algebra 2. That's doing some factoring on a fourth degree polynomial, and it's factoring that's similar to your quadratic factoring. The example on the right is also done by factoring, but it's a different method. The first thing you'd want to do is get everything onto one side. And after you get everything onto one side, you can recognize that you got four terms. This is an indication that we have to do factor by grouping. We can take an x squared out of the first two terms, leaving us with an x plus 1. We can take a -1 out of the last two terms, leaving us with an x plus 1. Now I've got two terms, and both terms have an x plus 1, so if we factor that out, we're left with what's in front. And I can continue to factor because we have a difference of two squares. Let's see if I can write that correctly. The x squared minus 1 factors into x plus 1, x minus 1. And then this would give us three real solutions, -1, and that would be of multiplicity 2 because you can see the x plus 1 factor shows up twice, and +1. So we're going to be doing the same kind of thing, only not with just basic variables like x, but instead with trig functions. So here's an example of a factor by grouping problem with trig functions. Your first step would be to move everything onto one side. And now we can factor out of the first two terms a 2 cosine of x, leaving us with a 2 cosine of x plus 1. The last two terms we can factor out a -square root of 2, leaving us with a 2 cosine of x plus 1. Now I've got two terms, and they both have a 2 cosine of x plus 1, so let's factor that out. Leaves us with what's in front, 2 cosine of x minus the square root of 2. Now we can set each factor equal to 0, and we get cosine of x equals -1/2. And we get cosine of x equals √2/2. Now if you go to the unit circle, to get your angles between 0 and 2 pi, cosine equals -1/2 at 2 pi over 3, and also at 4 pi over 3. And cosine equals +√2/2 at pi over 4 and 7 pi over 4. Four solutions to this trig equation. And those answers are between 0 and 2 pi. Next example is a little bit different. Finding all solutions again between 0 and 2 pi. This particular one, you've got 1 minus cosine of x on the left, you've got 2 sine squared of x on the right. I want to have just one trig function throughout the equation, so only having cosines or only having sines or only having tangents. So what I'm going to do is I'm going to substitute out this sine squared using a Pythagorean identity. Sine squared is equal to 1 minus cosine squared. And now I'm going to distribute the 2 and move everything to one side and solve it like a quadratic equation. Since my squared term's on the right and it's negative, I'm going to move it to the left. And now to solve this, we're going to have a 2 cosine of x at the beginning of that factor and just a cosine of x at the beginning of the second factor. And then we're going to go with a negative 1 here and a positive 1 there to get this factored. Now we can set each factor equal to 0, and we get negative 1/2 and positive 1. Go to the unit circle. Cosine equals negative 1/2 at 2/3 pi, as well as 4/3 pi. So 2 real solutions to that part of the problem. Cosine equals 1 at 0. So it looks like we have 3 solutions to this problem. Next example is very similar, but you can see that I don't have a square on either of these functions, so I can't use a Pythagorean identity. But what I'm going to do is I'm going to take both sides of the equation, and I'm going to square both sides, and that will allow me to use a Pythagorean identity so that I can get one trig function throughout the equation. Now when I square the right-hand side, try not to make an algebra 2 mistake and write sine squared plus 1. I call that an algebra 2 mistake because what you just did on the right-hand side, if you do that, is you're doing the F and the L of FOIL. You're forgetting about the O and the I. So please remember to FOIL it properly. So if you FOIL it properly, the middle 2 terms should give you negative sine x. That would combine to give you negative 2 sine of x. So that's the O and the I combined. And then if you do the last terms, you'd get positive 1. And now I can use a Pythagorean identity and get rid of this cosine squared, changing that into a 1 minus sine squared. And now we need to get everything onto one side. Let's move everything to the right. And if I do that, I should have 2 sine squared minus 2 sine of x. And I think the ones just cancel, so we've got a binomial. And we can factor that binomial by taking a 2 and a sine of x out, leaving us with a sine of x minus 1. Setting each factor equal to 0, we'll get sine of x equals 0, and we'll get sine of x equals 1. Sine equals 0 at 0 and pi. There's 2 solutions. Sine equals 1 at half pi. There's a third solution to this equation. Next example is very similar to the last one. I want to get one trig function throughout, and here we have a cosecant and a cotangent. So let me take this cotangent and move it to that side, giving me cosecant of x equals 1 plus cotangent squared. Oops, we don't have a squared. 1 plus cotangent of x. Now what we're going to do is we're going to square both sides. And in squaring both sides, that'll give us a cosecant squared equals, now again, you got to FOIL this properly. Try not to make an algebra 2 mistake. You're going to get 1 plus 2 cotangent of x plus cotangent squared of x. We'll now get rid of this cosecant squared using a Pythagorean identity. And cosecant squared is equal to cotangent squared plus 1. And now, to finish this problem, it looks as if the cotangent squareds will just cancel each other out. It looks like the 1s will cancel each other out. So we're left with 0 equals 2 cotangent of x, which just means 0 equals cotangent of x, because I divided both sides by 2. And now you don't have cotangents on the unit circle, so if you've got 0 equals cotangent, you have to reciprocate. The reciprocal of cotangent is a tangent. The reciprocal of 0 is an undefined. So now if you go to the unit circle, you've got undefined values at the top at 90 degrees, and also at the bottom at 270. So the answers in radians would be half a pi and 3 pi over 2. So this is solving additional equations involving trig functions, solving trig equations.